Hi folks, we're going to talk about queuing theory. Okay, now this sounds like it could not be more boring because it's literally the science of waiting in line. Um, However, it's actually kind of cool, I think. I don't know. I mean, it's just my opinion, but I think it's rather cool. Um, uh, the idea is we can use the Poisson process that we were talking about in the previous lecture to model both people coming into the line or coming into a store or getting online at the store, and also we can use it to model the process of the cashier ringing people up. We can imagine that whenever the cashier or the bank teller or whatever finishes ringing someone up, that counts as an event, and that those events also are like a Poisson process, that they happen with a certain mean number of events per unit time, but otherwise they're more like they happen at random moments. Okay, let's see. So maybe for simplicity, I'll think of this as being a bank, and we have customers coming in from outside. Now, this is what here I'm going to think of. These are the customers outside the bank, and they're on their way to the bank. And when one of these red dots arrives at the front door of the bank, which is the blue line, then customer enters, right? So we can think of this vertical line here. This is like the Poisson process, and the red dots are events. They're customers entering the bank. And at a bank, you don't really look around the store very much. You just kind of head almost directly to the teller, right? So once people come in the bank, then they line up for the teller. And so here's the queuing system. We've got these people here. Let's see. We've got these people who are in line, and then we've got this person here who is actually with the teller. Oh, and by the way, for the sake of simplicity, we're going to imagine that there's only one teller, which is kind of unrealistic, but nevertheless, it'll give you it's just slightly easier to think about it that way. It's not hard to model the situation where you have more than one teller. You can just change, for example, the rate at which customers are served by the at the cashier, at the teller, right? You can just increase the rate at which customers are served if you have more than one teller. Okay, so let's see. Oh, by the way, the entire system here, the people in line and the person currently being served by the teller, that's called the queuing system. And the people who are waiting to get to the teller, I'm going to refer to as the line, right? So that's basically just the number of people in the system minus one. It's kind of a useful distinction, although it's also kind of irritating, admittedly. Let's see. Okay, so let's get our constants, our parameters set up. Lambda is going to represent the average number of customers who get online per unit time, right? So maybe for the sake of argument, we could say unit time is like an hour or something. So lambda is the average number of customers who come in the bank and get online in the course of an hour. And mu, on the other hand, will be the average number of customers who are served by the teller in the course of a unit time or an hour. And we assume that mu is greater than lambda. That's kind of an important assumption because certainly if mu is less than lambda, that means customers are coming in faster than they can be served. So in that case, the line is going to grow to infinity, and it's a hopeless situation, right? So an essential assumption is that mu is bigger than lambda. I guess what happens when mu equals lambda is a little bit dicey. It might depend on random things, right? That would mean that the teller is just barely able to keep up with the customers coming in. But in practice, the chance of two random real numbers being equal is essentially zero, so we don't really have to worry about that possibility. And now, what we'd like to do is develop a theory for this queuing system that would answer questions like the following, like how long is the line on average, and on average, how long must a customer wait either to get out of the bank or just to get to the teller? I guess you could say customers are probably most impatient when they're in the line, and that their impatience subsides somewhat once they actually get to the teller and the teller is taking care of them. So probably if you're the manager of the bank or the store, you probably are more interested in reducing the length of the line. That's probably your main concern, is making sure that the length of the line is short. Okay. Now, let's see. So here's what we're going to do. We're going to break the time up into small increments, right? Small time increments. So over here I've got a horizontal line that represents time, and I've broken it up into tiny increments. So we can imagine that each one of these intervals here is of length dt, right? Some infinitesimal time interval, right? Whatever infinitesimal means, we won't worry so much about that, but some very small time interval in which you can be sure that at most one event is going to occur. It's such a small time interval that we can be virtually certain that two events can't happen in that short a space of time. And then what we're going to do is, on that time interval, and looking at comparing those two adjacent time intervals, we're going to study the values of these constants p, which represent the probability that there are a certain number of people in the queuing system. So p sub I, is equal to the probability that the number of people in the in the queuing system is equal to I. Right? Well, n is a random variable, right? So n is can be any natural number from 0 up to as large as you want. It represents the total number of people in the queuing system, and that's of course determined by a random process, by exactly how the bank has been operating, right, since it opened, right? That random process determines the value of n. And then, as I said, each one of these small subintervals I sub k is an interval of length dt, we're going to look at I sub k and I sub k plus 1, and we're going to look at how the values of, to start off with, we'll look at how the values of p0 and p1 are related on the time intervals ik and ik plus 1, right? So, let's see. So the basic idea is that, let's see, we want to say that one possibility here is that, well, here's the question. How could it happen that the number of customers in the queuing system is 0 at time I sub k plus 1, right? So there's actually really only two ways that could happen. That you could happen to have 0 people in the queuing system at time I sub k plus 1. The simplest way is if there was also no one in the queuing system the moment before, at the time interval I sub k, and that nobody came in. Right? Nobody entered the bank in that tiny time interval. But one other thing that could have happened was that you did have someone in the queuing system at the previous time interval, but one person, that one person got served in that small time interval, and therefore there was nobody in the system at the next time interval, I sub k plus 1. Okay, so there's two possible situations to consider. Now, in the first situation, we'll just compute the probability that this happens. Well, p sub 0 by assumption, I mean by definition, is the probability that there was nobody in the system at the first time interval, right? So that's this probability, right? That there was no one in the system at time I sub k. And then we also want to assume that nobody entered the store in that time interval. Well, if you recall from our discussion of the Poisson random variable, the probability that no event occurs on an infinitesimal time interval is basically this. It's 1 minus lambda dt, right? So dt is the infinitesimal length of the time interval. Lambda is the rate at which events are happening. Lambda dt is basically the probability that you get one event, or in other words, that one customer enters the store in this time interval here, right? And therefore, the probability that no one enters the store is 1 minus lambda dt. Right? The complementary probability. So we multiply these together, and this whole thing is the probability of this scenario unfolding, that 0 people were in the store the moment before and no one entered. So that's one way that the number of people in the store could be 0 at time k plus 1. The other way it can happen, though, is that you might have had one person in the store initially, and then one person was served by the teller. Well, the probability that there was one person in the store is P1. Again, by definition, P1 is the probability that there was one person in the store at time I sub k. And then in order for the number of people to be 0 at the next moment, one person had to be served. Now, customers are served. That's an event that happens with Poisson parameter mu, or with probability density mu. So the probability that one person was served, that's how I indicate one person is served. It's a red arrow going out of the bank, right? Probability that one person was served is mu times dt, right? And we're kind of assuming that nobody entered the store. The probability of that is 1 minus lambda dt. I just put that in for the record, but as you'll see in a second, it doesn't really matter whether we include that factor or not. But okay, so we're saying that one person was in the store, nobody came in, and one person was served by the teller. We just multiply all those probabilities together. Okay. Now, one other thing I want to comment on is that I mentioned that when you're working with Poisson processes, you can always assume that two events do not happen simultaneously, or even that basically two events never happen within the same infinitesimal time interval. Right? The probability of that would be second order. If the probability of one event happening is lambda dt, the probability of two events happening would be lambda squared dt squared, and this second order factor, term dt squared, we can regard as so much smaller than dt, it's negligible, right? So we can ignore that. And the same thing applies if we have, if we're contemplating a customer entering the store and a customer being served by the teller. That would be lambda dt times mu dt, so that would be lambda mu dt squared, and that's what we actually get here. Right? If we were to multiply these terms out, we would get a term here. Let me change color. Let's see. We would get a term here that looks like lambda mu dt squared. But we're going to ignore that because that's a second order term. So that's why I said that it doesn't really matter whether you include this factor or not. What this is basically just going to boil down to is simply, once we just disregard the negligible second order term, this is simply going to be P1 mu dt, right? And that's simply going to be the probability that that one person was in the store and one person was served, resulting in no one in the store at the next moment. Okay, so now if you put this together now, let's see. The total probability that there was nobody in the store at this time k plus 1, well, that's also P0, right? P0 is the probability that there's no one in the store at any random moment, right? So it's also the probability at the time k plus 1. So P0, probability of nobody being in the store, is equal to, well, it must be equal to the only two ways that you could have gotten no one in the store, right? And the only two ways that could happen is if first no one was in the store and then no one entered, or one person was in the store and then one person was served. And when you add these two terms up, so it's going to be this term and this term, you add them up and do the algebra and you get this relationship, right? Very simple. P1 is equal to lambda over mu times P0. Remember, by the way, that lambda over mu is, what am I doing here? Okay. Lambda over mu is less than 1, right? So that's going to be kind of important. So P1 is necessarily going to be smaller than P0 under our assumptions here, right? Okay, so that worked out nice and smoothly, right? P1 is simply lambda over mu times P0. Now, you can repeat this procedure for P1 instead of P0. So in this, what I did here was I got a formula for P0 right here. But you can repeat this scheme to get an equation for P1. Or for P1, and we can relate it to P2. Right? So that's what I'll do on the next slide. Okay, so now we're gonna look at the situation. How could it happen that the number of people at time k plus 1 is equal to 1? Well, that's just slightly more complicated. There are three ways that can happen. You could have nobody in the store at the previous moment at the time interval I sub k, and then one person could enter. Right? One person could enter the store. And we don't really have to worry about whether that person was served already, because it's probably that somebody enters and is served in the same moment. Again, that would be two Poisson events in an infinitesimal moment. We can disregard that. The other possibility is one person was already in the store, and no one entered and no one was served. And the third possibility is that two people were in the store, and one person was served and therefore left, and that reduced us to 1. So we got these three possibilities to consider. Now the probability of the first scenario is P0, which is, let's see, let me use some color coding here. So P0, that's the probability that there was nobody in the store in the previous moment. And then times lambda t, which is the probability that one person entered the store, or probably that one person entered, right? And so I used the green arrow coming in to mean somebody entered the store. Right? And by the way, because as we saw, P0 is equal to, P1 is equal to lambda over mu dt. Of course, that also means that P0 is equal to mu over lambda times P1. And if we substitute that in over here, then we get this expression. Right? So that'll actually be a little more convenient to eliminate P0 from the equation. So we can say that this first scenario has probability P1 mu times dt. Okay, second scenario. We started with one person and no one came in and no one was served. So P1 is the probability, P1 was the probability that one person came in, that one person was in the store initially, and then the probability that nobody came in, well, that would be 1 minus lambda t, and the probability that no one was served, no one was served by the teller was 1 minus mu t. Okay? And then the third scenario, well, the probability that there were two people in the store initially is P2. The probability that no one came in is 1 minus lambda t, but the probability that one person was served, that's the red arrow pointing out, that probability is mu dt. Right? So we multiply those together. Okay, so now we can say that the overall probability that that there's one person in the store at time k plus 1, and so technically the left side of the equation here represents what's happening at time k plus 1, and the right side is what happened in time k to produce that result at time k plus 1. So, in order for there to be P1, one person in the store at time k plus 1, which is probability P1, then either there was nobody in the store and somebody came in, or, so that's that, or there was one person in the store and nobody came in or was served, or there were two people in the store and nobody came in but one person was served. So now, once again, we multiply all this out, do the algebra, simplify all this, and don't forget we're going to drop all the second order terms. So for example, over here, when you have the 2 dt's multiplied together, we're going to drop that term, and over here, when we have these 2 dt's multiplied together, we're going to drop that term. So you only end up with, so for example, in the first case, we're just going to end up with, we're just going to end up with P1 minus P1 lambda dt minus P1 mu dt. Right? And here we're just going to wind up with P2 minus P2 mu dt. And the other terms are all second order terms. Right? So we ignore them. Okay, so that's where we got, that's where we got this over here. We added all those terms up. And then do the algebra again, and what do you know? You get exactly the same thing we got before, exactly the same relationship. We find that P2 is equal to lambda over mu times P1. Right? It's the same factor of lambda over mu. So P2 is in the same relation to P1 as P1 goes to 0. And it's not much of a stretch, I think, at this point to say that if you do the analysis in general, you'll find in complete generality that pk plus 1 is always equal to lambda over mu times pk. Right? And again, lambda over mu, that's a number that's less than 1. That's kind of important. Okay? So we've got this sequence of probabilities, P0, P1, P2, P3, etc., and each one is lambda over mu times the previous one. And that forms a geometric sequence. So we know that the probabilities form a geometric sequence. Each one is a constant factor times the previous one. Right, so we've got this, right? This is the general form for pk. That is one way we could write it out is we could say, as long as we know what P0 is, then we just have to multiply by lambda over mu k times in order to get pk. Right? So we can write out exactly what pk is in terms of P0. Right? So in other words, all we have to do is somehow figure out what P0 is in order to determine all the probabilities, all infinitely many probabilities. So, now this is actually a standard probability distribution, a geometric distribution, where you have the random variable can take any value from 0, any value from the counting number 0, 1, 2, 3, etc. And the probabilities are given by a geometric sequence. And there's a standard formula for the mean in this case, and there's a standard formula for what P0 has to be also in this case. But I'll just work it out from scratch. If you happen to have seen this in probability theory, you can just look it up actually. But if we want to figure out what P0 is, one way to do it is to use the fact that we know the probabilities have to add up to 1, right? The whole sequence of infinitely many probabilities have to add up to 1, and so we just do the summation, right? So we do the summation here. Pk is equal to this. Pull out the P0. The P0 doesn't depend on k, so we can pull that out from the sum. And then what's left inside is just a pure geometric sequence that is starting from 1, right? So this is of the form, this is a geometric sequence of the form 1 plus r squared plus r cubed, etc. And you probably know how to add this up. This sums up to 1 over 1 minus r, right? That's the infinite sum in that case. So then you just plug that in. Of course, r is equal to lambda over mu. So you just plug that in, and we get this formula for the sum is equal to this. And of course, on the other hand, we knew that that has to be equal to 1. Oops, that has to be equal to 1. Right? Has to be equal to 1, and therefore we figure out that P0 must be equal to the reciprocal of this number. And so P0 must be equal to 1 minus lambda over mu. It must be equal to the reciprocal of that number, right, if you solve for P. And, okay, so we figured out what P0 is. It's 1 minus lambda mu. And Pk is, of course, plugging everything back in over here. In the original equation I write down for pk, it's equal to lambda over mu to the k times the value of P0, which we now know is 1 minus lambda over mu. Incidentally, there's another more intuitive way to get this. Let me just sketch this argument. You could say that, look, I figure on average there's going to be lambda people who come in per hour, right? And put yourself from the point, look at it from the point of view of the teller, right? There's lambda people who come in the course of an hour, and I can serve mu of them. That means I can serve one person in 1 over mu hours. So the number of people I can serve in an hour, the number of people I expect to serve in an hour is lambda, and it takes me 1 over mu hours to serve each one of them. So therefore, lambda over mu would represent the amount of time I spend working. Right? I have to serve lambda people on average, and it's going to take me lambda units of time on average per customer. Oh, I'm sorry, 1 over mu units of time per customer. So the amount of time I spend working on average, right, the average amount of time working is lambda over mu. And therefore, we could say that, look, that makes it obvious. Therefore, the amount of time I don't spend working is 1 minus lambda over mu hours. And the amount of time I'm not working, well, that corresponds to the amount of time that there's nobody in the queuing system, right? If there's anybody in the queuing system, then there'll be somebody at the teller, and I have to work. So you can actually get this on a much more intuitive way by doing that. But it's also nice to see that you can get it using standard mathematical methods, right, by summing a series. Okay, so now that we've got the pKs, we know all the pKs, now we can go back and we can answer some of those questions that we posed initially. Like, for example, on average, how many people are in the queuing system? Remember, I think we used n to represent a random variable representing the number of people in the queuing system, right? So the number of people in the queuing system was n. So what we'd like to get is the expected value of n, right? Well, the standard way to get the expected value is you sum up the value of k, the value of n, possible value of n times the probability of that value occurring, right? So you just, in other words, you weight each possible value of n by its probability, and that's how you get the mean, right, or the expected value. Well, once again, I should point out that because a geometric distribution is a standard one, you could just look this one up, you might remember it. But again, I'll just do it from first principles here. We'll calculate the sum. So how do we calculate this sum? This guy here. Well, once again, okay, first of all, let me just plug in the formula for pk, right? So pk is lambda over mu to the k times p0, which is 1 minus lambda over mu. Now, let's pull some stuff out of this sum. I can pull out anything that doesn't depend on k, so I'm going to pull out the factor of 1 minus lambda over mu. I'm also going to pull out one factor of lambda over mu, and I'm going to leave k minus 1 factors of lambda over mu behind. Okay, but I can do that because what I've pulled out does not depend on k, so it's a perfectly legal thing to do. But now when you look at this sum here, look at this sum, you can see it's of this form. Right? It's of the form k times some constant raised to the k minus 1, and we're summing it now from 1. Oh, by the way, I changed the sum to go from 1 to infinity instead of 0 to infinity because, of course, when we're multiplying by k here, right? So when k equals 0, the first term just disappears, right? So we may as well just start the sum at 1. Okay, so this sum that we're working at here in this green box is the same as this one up here. And the one trick, I'm kind of fond of this trick. It's maybe a little bit dicey because we have to differentiate an infinite series, but I think you did this in calculus. It is valid, although it's not quite so easy to prove, but it is valid to differentiate a uniformly convergent power series. So here's the thing. This expression, k times r to the k minus 1, that's the derivative of r to the k, right? Those two expressions, the derivative of r to the k with respect to r is equal to k times r to the k minus 1. So what if we just differentiate this whole series over here? Well, the thing is, we know what this series is equal to. This series, the sum of r to the k is just equal to 1 over 1 minus r. And we know how to differentiate that. The derivative of that is simply 1 over 1 minus r quantity squared. Right? So you can check, you have to use the the chain rule, so it's 1 minus r to the minus 1, then you differentiate, you get minus 1 minus r to the minus 2, but then you have to multiply by minus 1 because of this minus sign here. Okay, so it comes out to be 1 over 1 minus r squared. So I can plug that back in over here, right? So now that we know what the sum is over here, I'll plug it back in over there. And in our case, of course, r is equal to lambda over mu. And so now we've got a nice closed form for the expected value. We got rid of the sum. By the way, you can see that one factor here, one of these factors is going to cancel. And then also when you multiply mu into the denominator, you're going to get mu minus lambda. So you end up with this. So this is equal to the average number of people. Once again, this is the expected value of n. It's the average number of people who are in the whole queuing system. I'll just point out that although I'm fond of this trick of using the derivative in order to evaluate this sum here, you can actually do it using more elementary methods. You can start off with what we know, that the sum of the geometric series is equal to 1 over 1 minus r, and then you can say, well, look, we're trying to figure out this series. We'll call it S2, which is 1 plus 2r plus 3r squared plus 4r cubed, etc. And then it turns out that when you compute S2 minus r times S2, you're left with exactly S1. Right? So S2 times r times S2, you just shift all the terms over, but then when you subtract, the difference between them is exactly S1. And the nice thing about this is now you just have an algebraic equation that you can solve for S2. So you can solve for S2 without using any calculus, just doing some algebra and plugging in, and of course you get the same result. Right? So anyway, that's kind of nice. Okay, let's see, what did I do? Okay, so next page. Another question we might want to ask is how many people are in the line as opposed to in the queuing system, in the whole queuing system. Now remember, so the people in line are the people who are waiting to get to the teller. Now normally, the number of people in line is equal to 1 minus the number of people in the system. However, that's not true if there's nobody in the system, because then, if n equals 0, then n minus 1 would be negative 1, but there's never negative 1 person in line, right? So we have to be just a tiny bit more careful about this. So what I'm going to do is I'm going to define a new random variable, I, which is equal to 1 when there's somebody in the system, and 0 when there's nobody in the system. A random variable like this, whose value is always either 0 or 1, is called an indicator. Because you can just say if the value is 1, it indicates that something is true, and if the value is 0, it indicates that something is false, right? So this I is the indicator that there's somebody in the system. Okay, and now with that new random variable I, now I can say that the number of people in the line, L, is always equal to n minus I, because I is only equal to 1 when there's somebody in the system. Okay? And when there's nobody in the system, I is equal to 0, and therefore n minus I would just be 0. So, to find the expected value of L, we can use a general fact about expected value that you can split you can split expected value up over linear expressions. So, for example, because L is equal to n minus I, the expected value of L is the expected value of n minus the expected value of I. Now, we already figured out the expected value of n previously. It's this, right? Lambda over mu minus lambda. The expected value of I is very easy to figure out because there's only one non-zero value it takes, and that value is 1, and it takes that value with probability 1 minus p0, right? I is equal to 1 only when there's somebody in the system, and that is when there's more than 0 people in the system, so it's the complementary probability to p0. Okay, now just do the algebra and you come up with this. Okay, so that's the expected number of people in the line at a given, at a random moment in time. Okay, now next, suppose you're the manager of this store or bank. Maybe what you're more concerned with is not how long the line is, how many people are in line, but how long people have to wait. So you might be interested in this, and as I said before, people are probably more antsy, right, more impatient when they're actually in the line, and when they get to the teller, their frustration probably eases a bit, right? So what you're more interested in is how long does someone have to wait in line before getting to the teller or the cashier. Right? Well, okay, this is actually fairly easy to do because we've already done the hard work here. We know that the average number of customers in the line is this, right? Is lambda over mu minus lambda. So that's the number of customers, I'm sorry, not in line, but in the entire system, right? The average number of customers in the entire system is lambda over mu minus lambda. So that means if you're a random customer and you walk in the store at a random moment, the average number of people you're going to see ahead of you in the system is lambda over mu minus lambda. And now the question is, how long do you expect each one of those customers to take? Well, I already pointed out that because the cashier or teller is able to process an average of mu customers per hour, that means that each customer on average takes 1 over mu hours to process, right? So the rate at which the teller works is 1 over mu. And therefore, we just multiply the number of customers times the time per customer, and this will give us the average waiting time. So W is going to be the waiting time for a customer, right? So I should have made a note of that. Let's see. So W is the waiting time for a customer. Waiting time. Oh, and this would be online. So to be precise about this, this is the waiting time online before you get to the teller. Okay, so the average waiting time would be lambda over mu minus lambda times 1 over mu. And finally, the average time spent in the entire queuing system, including the time at the cashier or teller, would be this, the expected value of W, right, that we just calculated. So it would be this much plus, one more time for the cashier to service you, right? So you have to wait for everybody else ahead of you to be served, and then the cashier has to service you. So we just take our previous calculation and add one other term, I over mu, and then do the algebra. It actually turns out to be an even simpler expression. It's simply 1 over mu minus lambda. Kind of a nice simple expression, 1 over mu minus lambda. It's the difference between how many customers the teller can service and how many customers actually come in on average and take the reciprocal, right? So this is a nice simple expression. I kind of been trying to figure out an intuitive way to argue for this formula, but I failed. Anybody can think of a nice intuitive explanation without using any of the complicated calculations we just did. An intuitive explanation for why this should be the average waiting time? I'm all ears. I'd be very anxious to hear what you come up with. But those are the basic formulas then you use when you want to answer questions about queuing theory, right? So, you might be running a McDonald's or something, right? That's another kind of store, fast food store, where as soon as people enter the door, they get in line, pretty much, right? But you can apply this to any kind of store, really. So people might wander around the store looking for what they want to buy, but nevertheless, they're going to get online on the line for the cashier according to some Poisson process, right? Some random process with a certain average per unit time. And then you might want to say, well, look, how much will the waiting time for customers be shortened if I hire another teller, right? If I hire 2 tellers, then that kind of effectively doubles mu, right? If you have 2 tellers working, then basically you can serve twice as many customers per hour. So that's kind of like replacing mu by 2 mu, right? And so you can make estimates of how big a difference that would actually work using that would actually make by using these formulas, right? How big a difference would it make if you actually double mu, right? And then so you could look at this formula here and say, how does that change if I multiply mu by 2? Would it be worth it to hire a second cashier in order to reduce the customer's waiting time by that much? Right? And various questions like that you can answer. Okay.